PyTorch. What's up with it? We'll find out. This is Answer Everywhere, and we're looking at the PyTorch source code. We're setting a timer for 30 minutes, just to give ourselves a constraint and not look forever at this at the source code. Okay, so PyTorch is going to be huge. It's going to be technical. What we see in 30 minutes will just be scratching the surface. Or maybe it's not huge, but I think people know what PyTorch is. It's a machine learning library. They build themselves as tensors and dynamic neural networks in Python with strong GPU acceleration. We have an Android directory, which is a little bit interesting. Benchmarks, binaries, C10. I think there's probably going to be something like a source directory that has all of the, maybe Torch. This is what, Python. So yeah, Torch, Gen. I don't know what that's going to be about, but I think Torch is where I want to be. We have underscore C, which I'm guessing is going to be C code. I don't know if they use the, whatever this is called, the C Python interface that is well known and whose name I'm blanking on right now. FlatBuffers is kind of like proto-buffers, but with different trade-offs. It's a free software library implementing a serialization format similar to protocol buffers, Thrift, Apache Avro, SBE, and Cap'n Proto. Primarily written by, I don't know how you pronounce Walter von Ortsmerson, and open source by Google. It supports zero-copy deserialization. Okay, this makes accessing data in these formats much faster than data in formats requiring more expensive processing, such as JSON, CSV, and in many cases, protocol buffers. So it's like it's kind of like protocol buffers with different trade-offs, and perhaps similar to what we just saw in Ethereum. Although I don't remember exactly how Ethereum did that because we only looked at the file for about 2 seconds. All right, so this C file, we've got a profiler, whatever ONNX is, NVTX is probably NVIDIA something, NVIDIA transaction, and CPU stuff and that sort of thing. Maybe this is not the most interesting place to be. We have lots of underscores: library, functorch, inductor, lazy, numpy, prims. I don't know what all those things are. Strobe light, and we have a vendor directory. And then we have non-underscore stuff like amp. Amp could be important. Autograd, I'm going to guess, is some sort of auto gradient, maybe auto differentiation. CPU is perhaps for running Torch on the CPU. CUDA is probably for running Torch on NVIDIA devices, on NVIDIA GPUs. FFT is probably fast Fourier transform. We have func. This could be potentially support for like function objects or something else. We have futures. FX and JIT, these are going to be, I don't know what FX is. JIT will be just-in-time compilation. Legacy, we can ignore it. Lib might be important. LinAlg should be linear algebra. Masked, I don't know. Monitor, who knows? MPS, I don't know. Multiprocessing is a Python library for using multiple processors. I don't know what MTIA is. NN should be neural network. ONNX might be, the NNs might be neural network, maybe some like second generation neural network thing. Optim is perhaps optimizations. Quantization is, I'm going to guess, quantization. Signal. Sparse is maybe for sparse matrices. Signal, that could be any number of things. It could be like listening to POSIX signals. It could be like a QT style signals and slots mechanism. XPU is maybe like a GPU or CPU or something like that. Then we have a bunch of Python files in the root directory. including torch version storage, random script, some py.type. So I guess this is like typing information, library, hub, extension, and I guess I'll just ignore all these. Let's look at what ONNX is. An open format for machine learning models that enables interoperability across frameworks, tools, runtimes. Open neural network exchange. Okay, so this is some support for an open thing. And so we'll ignore that. Func has something interesting. JIT. Do we care about JIT? Let's not look at JIT. FX is what? FX technical overview. FX is a toolkit for pass writers to facilitate Python to Python transformation of NN.module instances. That might be interesting. Let's just focus on NN. We'll look at some of these other directories just to see if anything like really jumps out at us. Here's NN. I think that's where we want to be. It looks like it has multiple subdirectories, so it's going to be maybe pretty hefty. Sparse has semi-structured. We'll look very quickly at this. Sparse semi-structured ops. What are we doing? Sparse semi-structured tensor. This class implements the typo semi-structured sparsity as a tensor subclass. It describes a sparsity pattern where n in every 2n elements are sparse, depending on the data type. Okay, so subsparse data type quantization. I'm curious to look at quantize, but maybe we can just ignore the rest of it. We get rid of the torch directory. Autograd. I kind of want to see. Functional forward AD. Grad mode. I don't know what's going to be important there. Maybe variable is important. FFT just has init, which maybe has some behavior. But we'll ignore it. That leaves us with NN and ONNX. Get rid of Optim is what? These are like optimizers. Like we have Adagrad, Delta, Atom, I think is maybe the one that everyone uses, or one of the ones that everyone uses. We also have a generic optimizer.py. And then we are left with the files that I actually want to look at. And I'll pull NN into its own window. We have parallel QAT. I have no idea what QAT is supposed to be. Parallel is going to be for parallel execution. I don't know if this is going to be like parallelize across processors or parallelize across GPUs or nodes of a high performance cluster or whatever. I don't know what intrinsic is going to be. Attention should be support for neural network attention. Backends, I don't know. Modules might be interesting. I guess I'll just open these all. And see what we see, like the bear that went over the mountain. Here's cpp.py. I'm guessing that's C++ support. Common types functional. I don't know what functional means. We've seen a few functionals. Use grad and init and parameter. Maybe init.py. This is an init.py without the double underscores. This file contains utilities for initializing neural network parameters. So there is no grad star functions. These no grad star functions, rather, are necessary as wrappers around the parts of these functions that use with torch no grad. Okay. It seems like this is kind of like filler, but I'm not sure. Here's calculate gain. Return the recommended gain value for the given nonlinearity function. Okay. So if we have a function like the sigmoid function, what was it? Recommended gain? The recommended gain is 1. But if we use a ReLU, then the recommended gain is square root. Okay. We have normal underscore, which takes a tensor. Fill the input tensor with values drawn from the normal distribution. I'm not really sure what I'm looking at. We've got a bunch of stuff like Dirac, fill the 345 dimensional input tensor with the Dirac delta function. Preserves the identity of the inputs in convolutional layers. Blah, blah, blah. The arguments are tensor, a 345 dimensional torch.tensor, and some groups, which is optional. And we have an example. So create an empty tensor with 31655. Is that a 345 dimensional tensor? I don't know. We call init Dirac on it. And then we can also call it with 32455 and call init Dirac, passing in the number of groups, which is 3. Number of groups by default is 1. So how is this different? We have 24 versus 16. Okay. Let's see if we can find class torch. No, not class torch, class tensor. So I guess this is probably it. We have it. It's in functorch /dim __ init.py. So class tensor, which this has some like C code. We're importing functorch.c. And I'm guessing, well, here's underscore tensor. Fast path around slow wrapping, unwrapping logic for simply queries used by the implementation. ... Probably simple queries. You can ask for its dimension. If use C, do this, else do this. So C __ torch function. I think that C _C tensor is maybe the real implementation. So let's go back to _C. There's some tensor up top. From torch, import memory format tensor. What? What I want is a .c file, which maybe, no, maybe that's not what I want. Is it in functorch? Is cdef how you define C stuff? I'm not sure. Let's try Emacs. So we have some stuff in Dynamo, some CUDA stuff, C init py class tensor base. This seems to be it. Class tensor base. It says defined in torch /csrc autograd python variable.cpp. And so tensor base has stuff like whether it requires grad, retains grad. These are booleans. A shape, some data, which is a tensor. Some names, which is a list of strings, device, etc. Okay, so the tensor base, which I'm guessing is the base class of all tensor implementations knows, for example, which device it's supposed to run on and what shape it has. And whatever a layout is and the type of data, I guess, is probably what D-type is. And real and imaginary, I guess this is just splitting it up into real and imaginary tensors. T and H, I'm not sure, maybe, not sure. Perhaps transpose and something else. But we also have MT and MH and the number of dimensions, and a grad function, and a grad, and the number of bytes, and the item size. And you can ask to view func unsafe, which will do some stuff. I don't really know what that's doing, but that's something. And we've got a bunch of def CUDA stuff, like CUDA stream base, which has a stream ID, device index, device type, device, etc. Okay. I don't know what this is, but we have something that S is a type var S bound torch.tensor. Let's see if we can visit the tags. Did I not do tags? All right, well, never mind then. Where's the rest of the grep? We have tensor type, blah, blah, blah. We have tensor list, which has what? A class tensor, and has a tensor to list function. So what is this CSRC file? I mean, CSRC folder. This has C code. Look at that. Let's check this out in GitHub, because I didn't generate tags for this thing. Oh, CSRC must be C source. I guess I was supposed to know that somehow. Here we go. This seems like the real stuff. All right, so where's tensor.c? I guess it's in the tensor directory. We have Python tensor and Python tensor.cpp. Okay. Initialize binding, get default device. And so that's really not so interesting. What about the CPP? We have a struct for the PyTensor type, which has some PyObject type, a THPD type, whether it's CUDA, etc. We've got this tensor new function, which returns a PyObject. And it takes in a PyObject, or I guess rather a pointer to it. And we do some checking and check whether it's CUDA. And we're going to return a new THP variable wrap. And it's something about legacy tensor constructor and getting the tensor type dispatch key and scalar type. And we might handle th errors. Okay, so it seems like the tensor is mostly like a, so it's going to wrap the data structure, which obviously, and then it also has a bunch of metadata, like what type it is, which device it's going to run at, that sort of thing. And we'll keep C source open here, but we should see some like mathematics. I think that ultimately the math is going to run on the GPU. I don't know if the handoff from the non-GPU stuff to the GPU stuff is done in Python or in C, but we'll find out. So now we're back in Python. We're looking at nn/backends, and there's not really anything. We'll just have some function to get the backend. Although there was a init file that I've been skipping over these init files because I'm just so used to them being empty. But it seems like these init files have implementations, although this one doesn't. So I'm not sure where that backend stuff is. Intrinsic doesn't seem so interesting. Modules has things like batch norm, activation, conv is probably convolution, pixel shuffle, RNN should be recurrent neural network, and then transform should be, I guess like an implementation of transformers. Let's pull this modules out. We'll look at transformers, maybe upsampling and RNN. You look at linear, sure. Okay, so we'll just look quickly at some of these modules. Generate square subsequent mask. So this is for generating some mask, a square causal mask for the sequence. The mask positions are filled with float negative inf. I'm not sure why we're masking. I could think of a few reasons, but I'm not really sure what they're up to. So the transformer is a module, a transformer model. User is able to modify the attributes as needed. The architecture is based on the paper. Attention is all you need. That's the classic Google paper from, I guess, 2017. And you can configure the model in a bunch of ways. For example, the number of expected features, the default is 512. The number of heads in the multi-head attention, the dropout value, etc. And we have some examples, which these probably actually run as tests in the testing environment. So transformer model, you give it some parameters, and it just creates a neural network. And then I guess this is like a random tensor and another random tensor for the target. And then we have some we call transformer model on the source and target, and we get some output. What does the output do? I don't know. But we can also look at the constructor. The constructor has some layers. So a transformer encoder layer is the encoder layer, and we pass in some of the parameters that we pass to the constructor to the transformer model. We also have a layer norm, I guess a normalization layer, which is called encoder norm, and we set the self.encoder to the transformer encoder of encoder layer, num encoder layers encoder norm. And then we have a decoder layer, which should basically be the same thing. So we have a norm and a decoder, and we what? Yeah, we have this decoder layer, we have the norm, and then we pass them into a transformer decoder thingamajiggy. And then we reset parameters, set self.dmodel to dmodel, set self.nhead to nhead, and set batch first to the thing that's passed in as batch first. And then on forward, we have reference to ourselves because this is Python. And we have a source and target tensor and a mask. So we can mask stuff out for the forward operation. And a memory mask. These masks are all optional. Some padding masks, whether the source is causal, whether the target is causal, and whether memory is causal. And these are all they're all optional except for the memory. I'm not really sure what causal means in this context. And we get a nice comment. Take in and process masked source/target sequences. If a Boolean tensor is provided for any of the blah 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 mask segments positions with a something or other, where they true are not allowed to participate in the attention. It sounds maybe a little bit conceptually like dropout. Oh, sorry, I missed these messages. Hey, I'm glad you enjoyed it. Thanks, man. Yeah. Okay, so this is transformer. We'll maybe take a quick look at just like what the math looks like for this encoder thing and this decoder thing. So I guess we're just deferring to the layers, and those should probably ultimately be calling the functions in the base neural network thing. Here's upsampling. I just kind of want to get a glimpse at, like, are we building up in layers like we are in transformers? I'm guessing probably. Here's forward. Here's the constructor. We've got this scale factor stuff. Yeah, this seems different. Unless I'm looking at the wrong thing. Do we have layer? Yeah, okay. Well, I'm not going to look too closely at that because we're quickly running out of time. We have about 5 minutes left. Here's RNN. This is specifically a recurrent neural network. This is some base class. And what? You've got a similar arguments to the first, batch first, dropout. We also have things like input size, hidden size. I guess the recurrent neural networks have hidden layers. So this is like processing input arguments. And then the init function which is where we are, but eventually we get down here, we process like all the inputs or whatever, and we iterate over the number of layers. And I guess build it up layer by layer. For direction, in range, number of directions. The real hidden size is maybe proj size, or it might be hidden size, and we build up a layer and blah, blah, blah. And I guess we do that in a loop. And so on. And we'll ignore linear. And let's find just the standard neural network. And that'll be basically the last thing we look at. Probably init. This file contains utilities for initializing neural network parameters. Is this what we already looked at? Yeah, we've got this calculate gain thing. Uniform. Fill in the input tensor with values drawn from the uniform distribution. So is a neural network just a tensor of some sort, or are these just utilities? This might just be utilities. I don't know where the, let's see. Is there like a class neural? I misspelled ner. We have a class neuron type, which is in this native metal thing. And is there a class NN? We have class NN backend. And I guess like module, maybe we'll look at modules. Maybe that's the secret to understanding how the neural networks work. There's a module in C, module.py. Okay, so all right, so class module is the base class for all neural network modules. Your models should also subclass this type. Okay, so you import torch NN as NN and torch NN functional, and you extend your model as an NN module. Submodules assigned in this way will be registered and will have their parameters converted to when you call :meth to, etc. Okay. So we have training, which is a bool, and a bunch of underscore stuff like non-persistent buffers, set, backward prehooks, forward prehooks, etc., etc. This is maybe kind of like implementation detail stuff, which is why they're private. We have an init function, which is going to log some stuff. We're going to call this super init, potentially. We're going to call a bunch of attributes. Call superset adder instead of the typical self.a equals a to avoid module set adder overhead. Modules set adder has special handling for parameters, submodules, and buffers, but simply calls into super dot set adder for all other attributes. Okay, so we are setting variables basically in a kind of funny way. We've got this forward thing, which we've seen called. That's the thing you implement for like a forward, I guess, iteration step. And it's by in the base class, it's unimplemented. You can register a buffer, add a buffer to the module. This is typically used to register a buffer that should not to be considered a model parameter. This should not be considered a model parameter. For example, bash norm's running mean is not a parameter, but it is part of the module state. Okay, so running mean is probably maybe like kind of like a moving average or something, and so it's like state in some NN module that is not like a parameter or an input or an output or whatever. You can register a parameter, etc., etc. add module, get submodule. So it seems like the modules are the main building block. What is CPP? Have we looked at that? Let's also look at parameter, and then we'll call it a day, since our timer just went off. Here's C _ C init pi I dot in. I don't think this is where, I don't think I just opened this because it's not a neural network. All right, here's cpp.py. For whatever reason, I guess this is like a Python thing, but like all of these files open with useless information, like defining an ordered dict wrapper, a wrapper around a C++ ordered dict. That's not like the first thing you want to see if you're looking at this file. We have a module wrapper, which is a subclass of Torch NN module that wraps a C++ front-end module and delegates all access. That's all that's going on. That wraps a C++ front-end module. So this is for, I guess, wrapping C++ stuff in Python so that Python can access it. Yeah, here's functional. And I don't know what's going on here. We've got a big comment. What is this comment for? A doc string. This is like conv2d, I guess. This seems to actually be some code. So fractional max pool 2D with indices. Maybe we'll look at conv3d or conv2d. So is there any implementation or is it just a doc string? Yeah, this is like one of those repos where it's not clear where to find the actual code that does work. So some of it is doing a little bit of work, but it seems like everything's in the setup. And perhaps that's because the thing that actually does the work are the things that are going to run on the GPU. And but it seems like neither the C code or the Py code has like a clear amount of functionality yet. Here's grad.py. We've got some conv1d input. And what it's going to do? Compute the gradient of conv1d with respect to the input of the convolution. This is the same as the 1D transposed convolution operator under the hood, but requires the shape of the gradient with respect to input to be specified explicitly. And we've got also conv1d weight, and we're doing some real stuff. We're calling ops ATen convolution backward. Here, are we calling ATen above? Torch ops ATen. So maybe ops ATen is where I want to be. So is there any ops in the root directory? Not really. We have pt ops. What about ATen? There was ATen, right? Here. This directory contains the low-level tensor libraries for PyTorch. Okay, so this is where I wanted to be all along. I didn't realize ATen was the most important directory. Aten.c++. Aten is fundamentally a tensor library, on top of which almost all other Python and C++ interfaces in PyTorch are built. I don't know what THC is, but we have Aten here. Let's just take a quick look at THC atomics. Not sure. Devices, something. And then here's Aten, and Aten seems to be the place to be. And here we have ops, templates, XPU, accumulate type, backtrace, array ref, cache, tensor utils, device, blah, 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 expand layout, matrix ref. probably a reference to a matrix. Parallel, native, scalar, scalar op, scalar type, tensor. Did we already look at this ATen tensor one? We're just including a 10 core tensor. So is the real stuff in core? Okay, so at least here's a header for what looks to be real. We can do things like tensor ref, which I guess is, which I assumed was like a reference to a tensor. And we have things like has value, register hook. We have the Torch API class. Okay, so this seems to be a real tensor. And then what can we do with it? We have a named tensor, a range, scalar, tensor accessor, tensor base, tensor dispatch utils, variadic. I don't know what variadic is going to be about. Should we look at function in grad mode? Intern to strings. We have some like just-in-time compilation stuff. So here's function. So function is a struct. It has a function. A function is a pure graph with no implicit self-object bound. It contains schema information and the executor that manages the execution of this function. Method is a wrapper on an underlying function that also provides a self-object. So this is like some functional object. You give it a stack. And it's not a graph function. It says it's a pure graph. I don't know what graph means in this context, but there's some notion of graph. So we don't have time. We're like way over time. We don't have time to really look into ATen, but this is, if I were to look at this again, this is kind of where it would start. Let's look at what ATen graph is. Writing graph transformations on ATen IR. So I guess ATen has some intermediate representation. Since the ATen IR sits at the FX graph/graph module level, any transformations written for FX graphs can be easily applied to the ATen IR. If you're familiar with writing FX graph transformations, then this will be the same. Okay, so it seems like maybe FX, I don't know if FX is fundamental or if FX is like an add-on feature. Is it the kind of graph that it's talking about? A graph is a context manager that captures CUDA work on a CUDA graph object for later replay. See CUDA graphs. Is a CUDA graph like a computation? Getting started with CUDA graphs. The performance of GPU architectures continue to increase with every new generation. But how about you define what a graph is? All right, come on. Let's see if we can find a non-marketing site. Let's just ask the AIs. A CUDA graph is a way to group multiple CUDA kernels, functions designed to run on a GPU, and other operations together into a single unit for execution on NVIDIA GPUs. It essentially creates a blueprint or roadmap specifying the order and dependencies within these operations. Okay. So it kind of defines like a workflow with multiple kernels, I guess, presumably so that you don't have to like manage the kernels in the CPU. I'm guessing the GPU manages I'm guessing you send the graph to the GPU itself, and the GPU manages it. Benefits: reduced CPU overhead from launching kernels, improved GPU utilization by keeping it busy with a continuous stream of operations, and potentially better performance through hardware accelerated dependency handling. All right, so I'll leave that there. That's PyTorch. It seems like the ATen library is really where all of the cool technical stuff is. That wasn't obvious to me as I was looking through the code until really at the very end there. So we didn't get to see much of it, but we at least got to see like all of the work that PyTorch is doing, building on top of that library. We got to see a little bit of, for example, the transformer, how the transformers were built up, and really a lot of the library is about about managing information so that like the Python layer can talk to the C layer, and the C layer can talk to the GPU/CUDA layer, and I suspect that it's mainly written in Python to give, because that's what data scientists are familiar with, and so it's a big part of like why we need kind of all of this like metadata type information and like the management of state, and why there are all of these kind of like boundaries, because we want the efficiency of the lower levels, but we want to provide like a nice enough API for people at the higher levels. So that's all for me, and I will be back tomorrow, and we'll look at some of the theorem provers. Thanks for watching.